Okay, so good, we get into the last part where we discuss chiral symmetry. Chiral symmetry, a fermionic symmetry, and how to implement it on the lattice. First, we recall what chiral symmetry is in the continuum, and then we discuss how to if we can formulate the lattice regularization in such a way that the chiral symmetry is not badly broken. This is very important for regularization. I mean, you can always say regularize something, break all the symmetries, and then if they come back in the continuum limit, this is questionable. So, the main purpose of a good regularization is to preserve the symmetries as well as possible. You can never preserve everything, otherwise you would not need a regularization, but chiral symmetry, we will show that you can preserve the essential part of it. So first of all, the standard model and practically all theories of interest are bilinear in the fermion fields. So here we have psi bar psi, and then some kernels, some Dirac operator here in between, which can involve gauge fields. This is now for fermion mass 0. And in this case, we have an invariance under what I call chiral rotation, that psi and psi bar are both multiplied with such an exponential factor, where gamma 5 is in Euclidean space. Gamma 5 is simply the product of all gammas. There is no I here, so we have the same properties as Minkowski space. Gamma 5 square is 1. This is also Hermitian. Did not write this here. And then it anti-commutes with all the gamma mu. So if we perform this transformation here and here, and then we move the exponential factor to the other side, then the sign in the exponent changes. So let's say if we start here, we move that, then we get an e to the minus a gamma 5, and then it cancels. So we have invariance for any real parameter alpha here. Okay. Now we can introduce these chiral projectors. Chiral projectors is P plus minus, where we have 1 plus minus gamma 5 divided by 2. Now it is easy to see that if we square the P plus or the P minus, then we get the same object again. This is, let's say, okay, what is the 1/2? 1 plus minus gamma 5 squared. This gives 1/4, 1 plus minus 2 gamma 5, and then here the gamma 5 squared is plus 1, and so this is again P plus minus. So this is actually the definition of a projector, something which is invariant if you square it. You can also see that the sum of these two projectors is 1, so they project on complementary subspaces and capture everything. So summing here is obvious, that gives 1. And the product of them is 0, so they have these subspaces where they have no overlap. So this is, can you imagine this? We have a large space, and this divides, this projects in one or the other subspace of it. So if you apply this to a spinor field, then we get subspinors here of 2, this has 4 independent components, then we have 2 independent components which I call psi left and psi right. And if I do the same for the psi bar, then the convention is that the pi minus gives the psi bar left and the psi plus gives the psi bar right. This is the terminology. We will see that this makes some sense. If you write the Lagrangian here, this is just a 1, and this is a 1, so we can insert these factors. Then we get here a psi left, psi bar, psi right bar, psi left, psi right. And if we, for the moment, we forget about the mass, and we see what is left from here, we can drag this to the other side, and it turns into a P minus, and then it's a P minus square, which is 1, so we get here the psi left times psi left. But we do not get a contribution from here because of this property. And the other case, of course, this turns into a psi plus, so it gives a psi right times psi right here, but without mass they do not mix. If we look at the mass term, then the situation is different, because if we move this, it doesn't change, so it's the opposite, that the psi left and the psi right make a contribution, or the psi right and the psi left, and if we meet the same here, then they cancel. So in the kinetic term, we have only left-handed fermions, that's why this notation is useful. Our right-handed fermions, but they are completely independent. If we have a mass term, then they mix. So you can say for mass 0, they couple completely. They do not know about anything about each other, so they can be considered independent fermions, and we can perform independent chiral rotations. If we have the mass included, this symmetry breaks explicitly, and so this is the reason why we cannot write a mass in the Lagrangian of the standard model. The standard model in the electroweak sector, the left and right-handed fermions couple in different ways to the gauge fields, to the electroweak gauge fields. So if you include a mass, you include a different coupling to the gauge fields, and you break gauge symmetry. That's why a mass term you cannot include in the Lagrangian. That's why the Higgs mechanism does this in an indirect way without breaking gauge invariance. But however, if we now look only at the QCD, we forget about the electroweak sector. Then this is what we call a vector theory, because left and right-handed quarks couple to the gluons in the same way. So in this sense, it does not matter, so we can include this term, because this does not break gauge invariance. If we do a rotation here, the gluons do not notice this. So that means in QCD alone, as a separated part of the standard model, we can include such a mass term in the Lagrangian. This breaks a global symmetry, but this is not so bad, it is not a gauge symmetry. Now, if we have a QCD with NF, let's say, massless quarks, so we have this structure. This is massless, so the left, this is the set of left-handed and right-handed, all the flavors are included here and here. We can do independently a UNF rotation in the right-handed sector and in the left-handed sector, and the full chiral symmetry is then the direct product of these two UNF groups. This is actually the full symmetry that we have, but it is useful to split it into subgroups and to divide off the U1, the phase factors, and then we are left here with SUNF left and SUNF right. So if we rotate the phase factors in the same way, here then we have a U1 vector symmetry. Okay, that means left and right is the same, and this is linked to the barrier number conservation. This is a symmetry which is there in QCD, and then we can also have the opposite where we rotate left and right-handed phases differently. This is called the axial symmetry, and that breaks under regularization, under quantization. So this is an anomaly. This is okay. This can be demonstrated by perturbation theory that this cannot survive. It's an interesting effect. I think Sebastião is an expert on that, but he is not here today. But what we are most interested in here is this SUNF cross SUNF, which we call the chiral flavor symmetry. We understand that in this massless limit, the chiral flavor symmetry would break spontaneously. There is strong evidence for that. Okay, this is not the physical situation, they are not exactly massless, but numerically and theoretically we have strong evidence for that there would be a spontaneous breaking down to SUNF, where left and right-handed is the same. So we use the full set of generators of one SUNF group, that means NF square minus 1 generators, and that generates then NF square minus 1 number Goldstone bosons. And then it is the concept of chiral perturbation theory is to identify these number Goldstone bosons with the lightest mesons involved. So if we have NF equal to then this would be the pion triplet. Since the quarks are not exactly massless, they are also pick up a small mass, but they are still the lightest particles involved. So it's like if you have the symmetry breaking picture of this Mexican hat, you have here the minimal manifold. Now you break it a little bit, so this is a bit tilted. This is a bit like that. So an excitation takes a bit of energy to get here. These are the pion masses, but it is much less energy than climbing up the potential walls. This is the potential here. So there are still the lightest particles involved. So, and then this number 3 describes exactly the pions. And if you are a bit more daring and also include the strange quark here as quasi-massless, then we get an octet, 9-1, which is the pion triplet, the 4 kaons and the eta particle. So in the beginning people thought about this symmetry, and then this number here should be 4 and 9. And then they were puzzled why then eta should actually be included here, but it is much more heavy. It's more than 500 MeV, and this is about 130. So something is wrong. And now if we take NF3, then you can include the eta, but then there is an eta prime here, which is almost 1 GeV, which is again much more heavy than this, and people were puzzled why there is always one which is too heavy. And Toff first gave this explanation that if you split off these phase factors and only consider the SUMF, then you get exactly the right picture. So we have the massless fermions. They remain massless under gauge interaction because this symmetry here doesn't change. So there cannot be a renormalization effect which gives the fermions a mass thanks to this symmetry. This is a very important property. And so the zero mass is protected, and also a small mass remains a small mass, but this is all, let's say, written in the continuum without thinking about regularization. So if we introduce a regularization which destroys this property, then the mass can jump up a lot, and then we wonder, is this now an artifact because we're doing the regularization wrong, or is there no regularization that preserves it, and this could be a physical effect? So if there is no regularization that preserves the chiral symmetry, then we have a hierarchy problem. Then we have the problem, why are light fermions actually observed in nature? So if we do not find any regularization which preserves the chiral symmetry, then it would be very unnatural to expect light fermions at all, because they naturally, when the mass is renormalized to the cutoff scale of the system. So if you consider only QCD, we have this lambda QCD, something more than 200 MeV, and we puzzle why there are two quark masses which are 2 orders of magnitude lighter than this lambda QCD. Or if we consider the whole world, then we would say, well, the natural scale of the whole universe is maybe the Planck scale. Why do we have fermion masses which are much lighter than the Planck scale? So often people say the hierarchy problem is a matter of the scalar fields of the Higgs in particular, and in particular supersymmetry people argue with that. So if you can attach it to a fermionic partner, then it is protecting a chiral symmetry, and then it's natural to have light particles. But this all assumes that you have chiral symmetry somehow, and once you have interaction going on, you first have to show that you can preserve that all under regularization, otherwise the argument is not really valid. So one way to do so is called, which we will not go through in detail, I will just sketch it schematically, is called domain wall fermions. These domain wall people, they introduce a pseudo extra dimension, let's say an x5, between two limits, and they attach with some suitable technique. Here they have this x5, they attach the left-handed fermion to the 2-1 wall and the right-handed to the other wall, and then they say, well, we can pull, the real world is living here, okay, R4 or also Minkowski space, and if we separate them well enough, then the mass is actually, the fermion mass is given by this overlap between the two wave functions, and then this is getting very small. So this, in principle, this works, and then okay, let's say this is x5 0, and this is something large, and this is minus L. So if you make L infinite, then the mass would be 0, and you can make it very large, then it is something light. And some people argue that this is the observation of light fermions is therefore a reason why extra dimension could be physical, because you can implement it in this way. Now, okay, I've seen this argument a number of times for extra dimensions, but okay, I also give you a list of objections. First of all, this extra dimension is not a real dimension. It is in the 4 directions you have gauge fields. In this extra dimension, they only have the behavior of a free fermion in the sense of the Dirac operator, but there are no gauge fields in the extra direction. So it is a kind of an artificial construction. It is, you can put it kind of extra layers or so, but it's not really a dimension in the physical sense as this. So I would maybe not call it an extra dimension. Second, okay, we have learned also from the history of physics that regularization grids are usually not physical. Okay, so again, for instance, there's this Pauli-Villars mass which was introduced, and also in the 50s some people thought, well, this is maybe something real, maybe these particles exist. They are very heavy, so we cannot observe them, okay? But they would break the spin statistics theorem because they have the opposite sign in the 2-point function, but they are scalars, so there would be a strange object. Nowadays you see, okay, you can do the regularization in other ways, and there's nobody believes anymore that these Pauli-Villars particles are physical reality. And so if we introduce something new, then we first have to ask, can we not do the same without extra dimensions? Then I would not believe that this is a physical, there is a reason to assume that this is physical. And this is exactly the third point. We can actually achieve exactly the same effect by staying consistently in 4 dimensions, or in 2 dimensions if you wish, at any stage without ever introducing these extra layers or single dimensions, and therefore I would be a bit skeptical about this argument. This is an argument to believe that the extra dimension should really be there. So this is what we will demonstrate now, that we can achieve this explicitly in, also in 4 dimensions. And okay, now I get to the lattice formulation. Lattice, okay, I said now for convenience, I set the lattice spacing to 1, otherwise we have to write a lot of these factors which obstruct a bit the view of what is going on. And then the lattice action would be that we have here psi bar, psi, only the fermionic part of the action, and then some element, some block here between. I think before I called it M, now it is D, which sounds a bit like Dirac. And the gauge fields can be in here, and it depends on these points. And of course, if it is massless, then we would expect this structure, gamma mu times some function rho mu, which depends again on all this. Okay, this doesn't need to be the same mu, so I should maybe write here mu on these points and the gauge fields in here. Let us start with the free fermion. Free fermion is actually already instructive to show what the problem is. Free fermion means you can consider as a gauge theory with the special configuration where all link variables are 1. This is an allowed configuration, just a special case. And then we want to regularize this continuum Dirac operator here in a way that keeps it anti-Hermitian. This is anti-Hermitian, so we would regularize this derivative by going 1 step forward minus 1 step back. This is useful. If we go, for instance, 1 step forward to 0, then it's not symmetric. We get a phase factor in here, and so on. So then we break hermiticity properties. So that would be a disaster. Yeah? So this is the obvious thing to do. Just to illustrate this in momentum space. In momentum space, this corresponds to this P mu, and what we do with it, I will derive this in the next page, is that this P mu is now turned on in a sinus P mu. If we would take a one-sided derivative, let's say just 1 step forward minus 1, then we get here a complex factor, and this is the worst thing we can get. So this is the obvious ansatz, and we will show that this doesn't work, and that's why it is called the naive lattice Fermion. So first of all, to derive that, okay, we take the product of this psi bar and psi, each one with in momentum space now, and this is the step forward minus the step backward in the phase space divided by 2a. Here write the a, and then we have again this sum over x, which if we reduce it to this, oops, I think I forgot the e to the I. Oh, it's here. These factors here, this gives us again such a Poisson periodic delta function, and then we get psi minus p of psi p, and this here reduces to the sinus of a p mu divided by a. And to start with, this looks quite reasonable. So if we take a small, then this can say, well, this seems to reduce to the first term in the sinus. We get the p mu plus some higher order terms which go away in the continuum limit. So at first sight, this looks quite reasonable. However, that's why it seems there's a problem to it. And the problem is, if we now look at the lattice propagator, so this is then the propagator here. If we take, this is the inverse of this object, now let's say we multiply by this, so we can have a denominator which is well controlled. We see that we have the physical pole at momentum 0, but we also have unphysical poles where the sinus vanishes, and these poles are still inside the Bruyère zone. So if we say we define the Bruyère zone such that the upper bound is included and the lower bound not, because of that we include it only once, because we have only the 2 pi over a periodic copies, then we say we have poles not only here, this is the physical one, but also here, 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 whenever whenever each of the component is either 0 or pi over a, then we have a pole here. And so that means we get unphysical extra particles which are generated by the regularization. This is in 2 dimensions. In general, these are 2 to the d particles instead of just 1, and they spoil the physical results completely. So they call them 2 to the d species. And if we now make a bit smaller and approach the continuum limit, this problem doesn't go away. So this is really there to stay. So that's a serious problem in the formulation. They have to deal with it, and for instance, there is this axial anomaly which depends on this separation of left and right-handed. This will be destroyed because in this 2 to the d we always have the same number of left and right-handed, so we get really wrong properties. We can show this if we take the energy as a function of one momentum component. This in the continuum it would be like this. And on the lattice we need something 2 pi over a periodic, so this turns into this sinus, and then we have here an extra 0 in this, extra 0 in d, and which turns then into a pole in the inverse d here. So here we see that we have a problem, and the same problem we do not have for bosons. For bosons, we have this squared momentum squared, and this does not need to go to 0 in the continuum like that, in the lattice like that. It's 2 pi periodic. For the bosons we don't have this problem. The problem emerges because we have linear derivatives and not square derivatives. So this is seems like a simple observation, but it's a very tedious problem indeed. And the first way out was suggested by Wilson, I think in 1978, a long time ago. He suggested to take this naive formulation and add one extra term, which is basically a discrete Laplacian. So this is a second derivative here, which if you convert it into a momentum space, this is what we have done before. It's like the Laplacian that we had in the Poissonic operator. So we have then this AP, this is the momentum, the lattice momentum, a square p square. So this looks quite good. So we have an extra term which stays 0 in momentum 0. It is still 0, so it does not destroy the physical solution, But if we have the unphysical solutions at the edge of the Bria zone, if this is pi, we have here pi 1/2, this makes it non-zero. So the unphysical poles go away. This is good, and also this is order A squared, the rest is order A, so if we say, okay, we take the small a limit, then this term is getting less important, and then we recover the continuum limit. So this seems like a simple but successful recipe, but the problem is that this term here breaks explicitly the chiral symmetry. Chiral symmetry means that the Dirac operator anti-commutes with gamma 5, which is true for D naive, but this extra piece here commutes, it does not anti-commute with gamma 5. This is just a scalar here. So this is not true anymore. So D Wilson does not anti-commute with gamma 5 because this piece here does not. So then we have to think about the consequences. Nevertheless, this has been used a lot in simulations and is still being used. But it has problems. First of all, the quark mass is not protected against renormalization, additive renormalization anymore. And actually you can see this from here. This is the free case. If you go to the edge interactions, then these deltas here are replaced by the link variables. They are suppressed. They are in average smaller than 1, whereas this piece here is not suppressed. So this is a minus, so then we get here something like an additive constant here. The more gauge interaction you have, the stronger it is, and naturally this goes to the cutoff scale, so pi over A. And so here we have additive mass normalization. So if we want to simulate like quarks, we have to start maybe with some negative bare quark mass and try and tune that such that after the normalization it's getting close to 0. This is a tedious business, it's only approximate, and then for every time you change the gauge coupling you have to restart again. So this is certainly a severe disadvantage here. And also here you think that the lattice artifacts are of order A squared, but due to this effect here, once you have gauge interactions, they are all of order A. So that makes also the artifacts worse than before. So these are the disadvantages of the Wilson formula. Still, it has the advantage that it is very easy to implement in the code and it is user-friendly, so that's why it is still used. But then people asked since the 1980s, is there not an easy way to avoid these problems? And there is a famous theorem from '83 called the Nielsen-Ninomiya no-go theorem, which says basically if we assume discrete translation invariance, this is something that we should have, right? Then we assume that the lattice Dirac operator is anti-Hermitian, so that guarantees that the action is real. So we should not use, for instance, one-sided derivatives. So this is we also have to assume, and then we have to assume locality. So this usually drops to 0 at some distance. So you can say, okay, we can extend it by long-range couplings, but they should decay at least exponentially. There are theoretical reasons to say if you do that, then, or means in momentum space you have an analytic function, then you are in the right universality class, that means you get the right continuum limit. So this is what is called locality. And if you also assume that there should be no doublers, then you cannot implement chiral symmetry in this way. You will not find any D which anti-commutes with gamma 5 and which fulfills these 4 obvious conditions. And this theorem, okay, other people a lot say, okay, there seems to be no solution to it. And okay, we can illustrate actually the theorem quite easily. Let's say again in the free case, this is what we have as an ansatz. And we have to require the correct continuum limit, so this rho mu must be p mu plus some higher order terms are possible because the order A is suppressed. And then we can picture it. We say, okay, this is the rho mu as a function of one of the components. It must be odd, it must go through 0, and it must be 2 pi periodic, so here it must have the same tangent. Here you can deviate from the sinus, you can do something else, whatever you like, but there is no way to avoid that in the Fourier zone here between minus pi and pi, you cross this axis again, so you get an additional 0. So there is no way to avoid the doubles. So you can deform this curve as you like. Of course, it should be analytic in momentum space for locality. That's why you cannot introduce jumps. Of course, if you introduce jumps, then you can do it. And some people actually suggested that. The SNAP group, they say, well, just take the continuum dispersion relation at the edge of the Fourier zone into a finite jump, then it's periodic, then it is non-local. Then you give up locality, and then also Reddy suggested even an infinite jump here. Then it turned out that if you do this in perturbation theory, for instance, you see that on the one loop level, it does not reproduce the right anomalies and so on. So that's why these non-local formulations are not only unpractical but also conceptually wrong. So again with this picture, there is no way to avoid this. We have to, if we require locality, there is no way to implement the anticommutativity of d and gamma 5. Now, okay, I come to the solution to this problem, and this is known as the Ginzburg-Wilson fermions. So first of all, we accept the fact that this continuum condition cannot be fulfilled on the lattice. So we break this a little bit. And what Wilson suggested is that this anticommutator is not 0 but something local, like a discretized Laplacian. So that we can do something else. It's a Wilson type term, and we saw that this makes some problems. Now what the Ginzburg-Wilson fermions instead suggest to do is that we take the propagator, the inverse d, gamma anticommuter with gamma 5, and call this. This does not need to be 0, this cannot be 0 anymore, but this is something local. Then that piece here can be non-local. And if this is local, the advantage is that the poles in d to the minus 1 are not shifted by this extra piece. So let us look at this explicitly. So we have here this anticommutator, and I still multiply it with such a factor, and I call this a local term R. Now, okay, I can take this factor to the other side, and then I can multiply from the d from the left and from the right, then I get here the anticommutator of d and gamma 5, which is now not 0, but it is something two d's which sandwich a gamma 5 and such an extra term. The extra term can be put to 1/2 to make it as simple as possible, so that would be d gamma 5d. So you see that this, okay, if I write from the dimension, this has dimension R square, so it comes from with a lattice spacing factor, which I did not write because it is 1 in this notation, so this goes away in the continuum limit. And we have now a particularly smooth, we have broken this property, but not in the crude way as down here, but in a particular smooth way, which does not shift the poles in the propagator. And this is known as the Ginzburg-Wilson relation, written down in an old paper, which was then forgotten over a long time, and then rediscovered at the end of the 20th century. Now, why does this have such good properties? And this was pointed out a little bit later by Lüscher, that actually if you have this property, you have chiral symmetry even on the lattice, an exact chiral symmetry. It is just not exactly the same as in the continuum, but it's good enough to have one. So if we now perform the chiral rotations in this way, epsilon is something small, and up to here is what we have in the continuum, and now I add this extra piece here. Again, it's there would be a factor of A if I would write it, so this is something which comes in only on the lattice. And now I look at, this is the shorthand notation for the Lagrangian, I look at it after the transformation, so multiply with this factor, and only calculate to epsilon, then I get this from the left, up to here, and this with this factor up to here on the right. Now I get, from here I get minus gamma 5, no, from here I get gamma 5d, and then from here down d gamma 5, so this is the anticommutator of d gamma 5, and then here I get twice minus 1/2 d gamma 5d, so together minus this. So if the Ginzburg-Wilson relation holds, this is exactly the Ginzburg-Wilson relation. If this holds, then this extra piece is 0, and then that means we have invariance to order epsilon, and this is good enough because this is a Lie group rotation. If you have invariance to the leading order, you can proceed in small rotations, and you have exact symmetry under this modified transformation. And if you take the limit a to 0, this term goes away, and this then it turns into the standard transformation in the continuum. But the essential point is that we do have a continuous exact symmetry even in the lattice if we obey this rule. So historically it would have been maybe more obvious that somebody starts with this ansatz and checks what property you need to have this invariance, and then you would have discovered the Ginzburg-Wilson relation in this way. So we have a lattice modified chiral symmetry, but even this is enough to avoid order A artifacts, additive mass normalization, the mixing of observables and so on. So this is enough to guarantee all the good properties that we would like to have. And now this is still only the relation, then the question is still what solutions do we have to the relation? First, the way it was discovered in the 80s was by polymerization group transformations, which is a bit a complicated concept. We worked on that again in the 90s and rediscovered practically the same thing until we noticed that it was written in this forgotten paper by Ginzburg and Wilson. So if we plot variable transformations of the fermion fields, we find a solution, but I must say that the solution is not very practical not very useful for practical purposes. Then, around a bit earlier, Dave Kaplan has suggested the domain ball fermions that we mentioned already. Only after this relation, okay, with exactly this picture, after this relation was established, and people noticed that in the limit where this separation goes to infinity, this is actually also a solution to the Ginzburg-Wilson relation. But the simplest solution to demonstrate, and this is what I will do now, was given by Neuberger in '98, and he started from here and found a trick to integrate out this extra dimension and got then what he called overlap fermions. But there is a way to derive this much simpler than Neuberger did. I can rederive it in one page. Okay, he has written 100 pages about it, but I can rederive it in one page. If you know the Ginzburg-Wilson relation, I will show now how this solution works. This is actually the last thing to be done here. So, first of all, a Wilson fermion, and practically all lattice fermions on the market have a property called gamma-5 formation. That means if we sandwich it between gamma-5, d gamma-5, we get the dagger. So this is true for the Wilson fermion. Okay, here we have the naive fermion, which changes the sign with the gamma-5 because it's anti-commutes with gamma-5, and this does not change the sign, so we get exactly the Wilson dagger. And this is quite generic. So let us assume that our building block can be a Wilson fermion, it's gamma-5 formation. Now, and we also assume that the kernel of the Ginzburg-Wilson relation is the simplest object possible, is this 1/2. Then the Ginzburg-Wilson relation reduces actually to this property. I multiply, let's say, with gamma-5 from the left, then this here cancels, we are left with a d, this turns into a d dagger, and this turns into a d dagger d, so we have this very simple form of the Ginzburg-Wilson relation. D plus d dagger must be d dagger d. Mathematicians call this a normal operator, but it doesn't matter, it's just this condition. Let's say this is the simplest way to put it, and we search now for a solution to this, for an operator which solves this condition. The next thing is we make a simple substitution. We take A is d minus 1. Just shift it by 1, and if we now look at A dagger A, we get d dagger d minus these mixed terms plus 1. If this relation holds, the Ginzburg-Wilson relation holds for d, that means A must be unitary, right? Then A dagger A must be 1, so A is unitary. So we can also look at this A and say if we look for a solution of such an operator A which is unitary. And then if we take, for instance, the Wilson fermion, plug it in here, then we get a d Wilson minus 1. This is of course not unitary because we have this shift of we have this mass normalization and so on. But so it is not obvious to find this. But if we start from this, then the way what Neuberger did in a very complicated way, I will simplify it now a lot. We can simply enforce unitarity on this. What we do is we take this A Wilson divided by the square root of A Wilson dagger A Wilson, and this object here, which I call A overlap, this is then of course unitary. So A overlap dagger A overlap. Okay, you have these square roots here, then this gives 1. Yeah? So if we just divide by the square root, we have unitarity obeyed, and then we can extract the Dirac operator, we add this 1 again, and here we insert again the original, the Wilson operator here, and this is what the form that it takes. Here it looks more complicated than it actually is. It is just the crucial step is only dividing by the square root, and then we get this this operator here. And the spectrum of A, since it is unitary, it is located in the unit circle here, and then we do the shift +1 or +1 over A. If you write the lattice spacing, then it is on this circle, on such a circle in the complex plane. What we do, okay, the continuum, the spectrum will be on the imaginary axis, and now with this regularization it is on such a circle. But what is really important is that the zero modes here do not move away from zero. For any gauge configuration that you plug in, the zero modes are there to stay. They will not move away, and that means exactly there is no mass normalization going on. So the chiral fermion remains chiral under any gauge interaction. And moreover, the gamma 5 has then eigenvalues which have a chirality ±1. This is the spectrum of gamma 5, and this is known in the continuum as the fermion index. Since the zero modes are still exact, we have the same, we can introduce such an index also in the lattice, and there is a famous theorem, Matthias-Singer index theorem, which says this is the same as the topological charge in the continuum. Now if we have on the lattice such a fermion index, we can use this to define the topological charge on the lattice. So to start with, there are no topological sectors on the lattice. You can transform the configurations one into another continuously, but if you have chiral fermions, you have an index, and then you can say this divides now the configurations into subsets, and this is the best definition that we can give for topology of gauge field, of Young-Mills gauge fields on the lattice. There have been, before this discovery, there have been many other attempts to define it, but they were all conceptual on weak basis and didn't quite fit, didn't quite work. This is a completely clean definition to introduce topology on the lattice. This is what Sebastian asked last time after the talk, but now I'm answering, unfortunately, is not here. Okay. Now a question is of course, how about locality? We said we need an analytical function in momentum space. Now we introduce this inverse square root, so one could have good reasons to be worried about locality if this still holds. Actually, locality is the reason why we have to introduce this shift, because if we would divide by d dagger d, then we have the zero modes here, and we run into singularity, and then we have a problem that will not be local anymore. If we have this shift and we have relatively smooth gauge fields, then this will keep far away from 1, and this function will be controlled and will be local. So locality holds for smooth gauge fields, and not for all gauge fields. You can introduce gauge fields which are so wild that they make a problem here. But if you say, okay, I take a gauge coupling and then measure, for instance, the decay of the maximal correlation over some distance, one can see that statistically it holds if the gauge coupling is large enough, is smooth enough, so that it favors the smooth configuration. So if you have a high beta or a small g, then it works. And so we can, if we are in the regime, So in QCD a beta above about 6, then it works, and one can demonstrate that it is local. It is not a safe property, but if beta is large enough, beta is this coefficient in the exponent, then one can demonstrate statistically that locality still holds. Now we can consider this overlap formula as a kind of map of this of the spectrum here onto this circle, and this the circle has here radius and center 1 over a, and a to 0 is the continuum limit, and it returns to this. Okay, if you make it larger, it's like this, and then it returns to the imaginary axis. So all this gives a consistent picture. But if we want to compute this. This square root of an operator is a tedious object in practice. So what one has to do to compute it for a given configuration is to approximate this by a polynomial. And now in real life, maybe you want to approximate this to machine precision, or let's say a little less, order 10 to the minus 10. And then it can happen that we need about 100 orders of this polynomial to get it right. Can be done, but if we compare it to a Wilson fermion, then we have then a factor of 100 of extra computing time. So this is a disadvantage. It is much more tedious to compute, but it has much cleaner theoretical properties. And another final remark, a bit of propaganda of what I'm doing myself, is one can replace this Wilson kernel here, of course, also by something else. So we have, for instance, constructed a renormalization improved kernel, which is a bit, which is already approximate Ginsburg Wilson. So if we have this, then the square root is closer to 1. This is so if this is approximate, the square root would be 1 if this is Ginsburg Wilson already. Now if it's approximate, it is closer to 1. We have less problems with locality, and in fact we can see that it is much more local. We have also better scaling and rotation symmetry, so it approaches the continuum values faster thanks to this renormalization group improvement, but it is again more complicated. You have more couplings than the Wilson couplings in this kernel, which is in the square root, so it makes it again more complicated to simulate, but still this is something that we have worked out in recent time, and we can see there are advantages but also some problems to it. But just to see that, of course, here you can use, okay, what we do is simply that instead of this A Wilson, we use something better, which is also gamma 5 revision, but better from the symmetry properties, but unfortunately more complicated. Then it is again more complicated to evaluate the corresponding overlap operator, but we have then better locality properties and so on. So, and this is then the end. So, okay, this is the final slide. So, fortunately, our Colombian colleague has still disappeared. He wanted to do some simulations. If somebody sees him, tell him that okay, to send his results. And okay, so are there final comments? I know that it takes some time to reproduce all the details if somebody is interested, but I wanted to give the main idea, and yeah, so this is the idea. Was this is this captured well, or is there something which is completely unclear? Or?
No, it's just to try to understand all the procedures.
Mm-hmm. I return to a specific page, or okay, you tell me which one.
Topological page.
Ah, yeah, topological page. Yes, here. Okay. The Akira-Singer theory says that if you have gamma 5 times psi equals 0. Then you have eigenvalue, then you have, no, gamma 5 times psi is psi, then is plus minus psi, sorry, it's plus minus psi. Then you have, you find solutions, let's say 1 to some index with plus solutions. Let's say we have n plus solutions and minus solutions. Then the index of the Dirac operator for a given configuration, index of D of some configuration, some gauge configuration is n plus minus n minus. And the Atiyah singular index theorem says that the topological charge is minus the index of D. So this is the first side a bit surprising because you have in an equation something which has apparently nothing to do with one another. Okay, this is of course of a configuration. Okay, this is a configuration, and this is also of a configuration. The topological charge, if we define it directly, is something like, okay, we have F mu, dual. Okay, this is there is a trace over this, and then some normalization like I think pi square, where F mu dual is epsilon mu rho sigma F rho sigma. So this is the definition of a topological charge. It's kind of a binding number, right? If you have a very smooth gauge field, then this is 0, and then you say that the whole set of gauge fields is then divided into subsets which cannot, let's say this is Q equal to 0, Q equal to 1, Q equal to 2, Q equal to minus 1, etc. And if you do continuous transformation of a gauge field, then you will always stay in the same sector or here, but you can never get from one sector to the other. So this is like, let's say if you have a string here and you can bind it around an object, you can deform the string as you like, but the binding number here will always stay the same. It can be maybe 2 bindings or the other way direction, and so you can deform it a lot, but the binding number will stay the same. So in this sense, the index defines this, is identified with this winding number. This is a measure for this winding number. Now, it is of interest to know, for instance, the expectation value of the topological charge square. And perturbation theory has no chance to see it because perturbation theory is only involved here. You can say if you then expand not around the smooth, the zero field, but around an instantone field, then you capture some points here and here, but you only capture small vicinities, but not the whole sector. Now this is topological susceptibility is this divided by the volume, and there is a rule which says that this can be related, can be used to explain why the eta mass, eta prime particle is so heavy. Why it does not fit into this light octet, which has masses between about 100 and 500 MeV, but this has almost 1 GeV. And so to understand why this is so heavy, okay, we wanted to measure this, and we can only measure it non-perturbatively, but on the lattice, basically, first to start with, we don't have topologies because you can transform continuously. But now we have this index, this we can introduce. We have this n max and minus, we can introduce this on the lattice with this Dirac, with the Dirac operator, because these zeros are exact. The gamma 5 still have this property as plus minus 1. So we can for each gauge field, for each gauge configuration, we can measure this index, identify it with the Q top, and then do statistics, generate 10,000 configurations, measure this square expectation value, and we see that with this formula, this is called Witten-Veneziano formula, we can then in fact derive to some approximation this eta prime mass and say, okay, this gives a valid explanation why it is much heavier than the other light mesons in the business. So this is an application. Are you happy with that? Or yeah. Okay. Good.
Can you apply those techniques in other theories like gravitation, lattice gravitation?
Gravitation. Yeah, this is a difficult issue. What people did a lot is a kind of okay. You can in principle think of a quantum gravitation ansatz in this way. No? Then you can of course not start from a regular lattice because then you have anticipated geometry, but you can say, okay, you have some random distributed points which carry some fields and so on, and then you do some, you order them in triangles, and from the triangles you see the curvature of space-time. And people try to simulate that, and also with dynamics, where the dynamics is not only in the fields but also in the points, where in the geometry of the points. And actually the geometry only tells us how the neighbors are coupled to each other. So basically, I don't care if this point is here on the moon, but I just want to know how much strongly it is coupled to its neighbor. And then there was a fashion in the 90s to work on that, and now it has to a large extent disappeared because the main problem is that to find a continuum limit, right? Or once also here a continuum limit, if this is the spacing A to 0, that means actually we have A over correlation length to 0, so we have to find a second order phase transition. And people simulated and showed phase diagrams of this, but they always got stuck with only first order phase transitions. They never found a point where xi goes to infinite, a second order phase transition. So that's why there were in this community of people who did this, there was some frustration then after some time, and most of them now started to do other things because they never found this a proper continuum limit. And if you don't have this, then we cannot rely on this universality concepts that with different regularizations you get the same result in the final limit and so on, and then basically everything is out of control. And so it remains with the situation that we still don't have a good formulation of a quantum gravity approach. This has been a reasonable hope that this could be done in this way, but the main problem is that there was no second order transition. If you're interested, read the papers or the papers of Jan Ambjörn or Ben Peterson, these people have worked on this for a long time. Okay, sure.
What is the importance to find a second phase transition?
Second order phase. You see, the continuum limit. Okay, we have A is the spacing between the nearest points, and the natural scale of the system is the correlation function. Is the correlation length. Yeah, this measures how the points. The correlation between points here, phi x and phi 0, how this decays, right? This is the natural scale of the system. So if we say the continuum limit means that this has to go to 0. Limit. Now, since A you can put it to 1 in our formulation, we cannot really do much about it. We say this is just an input parameter, we cannot really change it. So we need to change the couplings of the system such that this psi goes to infinity. then this ratio here goes to infinity and the lattice spacing is getting negligible. So if you have this structure here and the lattice and the psi is something like that, so many orders of magnitude larger than A, then you can say now the regularization is not important anymore. Now it is negligible to compare to the correlation length, to the scale. So this is what corresponds to the continuum limit. Right? This is the only way. We're always interested in this point where psi is getting very large compared to the lattice spacing. This is the definition of the continuum limit. Now if you change how we have some couplings here and couplings, and you look at properties like the magnetization, squared and so on, you can see if you find such a second order phase transition should be a peak which goes to infinite in infinite volume. But if you have only finite gaps like this, but no peak, then it's a first order phase transition, then you don't have this property, and then basically you have no continuum limit, and then every different variant to put this on the lattice will give different results. And then you do not have this universality property. That universality means you have here many formulations to put the fields, and if you in this limit, then okay, here you have different results for different theories. If universality holds, then they all converge to the same limit here. This is A over psi. If you do not have this limit that goes to zero, you have just a mess of different results. You have no clue to say which is the correct one, and you don't have a proper formulation that you cannot take the physical limit of it. So this is not a detail. This is really important. Actually. Yeah. Okay.
If you use non-commutative values.
Oh yeah. Some people have. The Crossman variables. Yes. Yeah. This is okay. In the homework, there are lots of questions about this. I mean, the fermion fields psi. So they have here these components of x. So they are described by Crossman variables, and this is the only way to implement. We don't have these operators as in the canonical formulation. The whole idea of functional integral is to remove them from the beginning, and we have only coordinates. And then the only way to implement now this principle is to use coordinates here which are anti-commutative among each other. So you have this eta 1. Eta 2 plus eta 2, eta 1 is 0, or eta I, eta j plus eta j, eta y, I is 0, and which means even eta I square itself is 0. So to begin with, it seems to be a very drastic change in the concept, but then if you look at the functional integral, you see actually it doesn't change that much. So it's we have this situation here that we integrate over many of these variables, and here we have psi bar and some matrix psi, and we saw the result is determinant of this M. And if this would be a scalar fields, let's say complex Hermitian scalar fields, e to the minus phi or n phi, actually the only difference is that it is 1 over determinant A. Or if it's real scalar field, then it's 1 over square root determinant M. So you always get this determinant of M, and the different types of fields only change the power of the determinant. So it's not technically after all, it's much more similar than you would think in the beginning. But it's fun to play with this. Okay, a question is, for instance, in this Crossman integrals. Okay, we saw an integral e eta I, eta j. It's a delta ij. Then you can ask what is a delta function in this formulation, or can you perform integration by parts and so on. And so you can ask. And actually, it's quite easy. It's no long calculations. Just think and find the right idea. It's quite fun to do that. And okay, so they are funny animals, these Crossman variables, but everything is consistent with And okay, then people have also other concepts like Pfaffian and so on. So this is supersymmetry. They have then at once not only determinant but some at once properties that you have if you mix different kinds of fields and so on. But they also use this Riemann fields.
That calculation requires a supercomputer, so can be made.
It depends on the model. If you want to do, let's say, quantum electrodynamics in 2 dimensions, a Schwinger model, this you can do on the PCs here. If you want to do QCD, and you want to do QCD in a way that you can publish it in the 21st century, so it is competitive with other results, then you need supercomputer. Okay, you don't need it yourself, but you can apply for computing time at these large computing centers. You have to submit a proposal, and then it will be evaluated, and probably will be given some contingent, some time for 1 year that you can use. And it's not only time, it also takes people, so it takes some collaboration of 10 or more persons who write different parts of the code, must be done very carefully and so on. And so these large collaborations, this is now, from the sociology, is a bit more like experimental physics, so that people work on specific, students work on specific aspects, maybe one only on the data analysis and so on, and few people have the overview of what is going on. But if you want to do smaller projects, let's say for solid state physics or to check a conceptual property, then this you can still do also on PC, on a PC cluster, let's say. And this is so. For instance, in Mexico, I've now installed 32 cores of special purpose that we can use. So with this, we can already do nice work. Not QCD, but so some other projects to check conceptual properties we can do quite well on small machines. So of course this is what 10 years ago even that would have taken a supercomputers, but today PCs or small clusters so on are so powerful that you can do a lot of things with them already. It's kind of more democratic because many people, even with modest resources. This is not such a cluster of, let's say, 100 cores is not so expensive. Basically, every university can buy that. Compared to experimental physics, this is almost nothing. So basically, everybody can do this. Maybe not exactly QCD, but other bit simpler models can be simulated.
No, we didn't have single model.
Yes. For instance, if you're interested in a 2D O3 model, this you can do very well on a PC. Yeah. And it's not only a matter of the computing power, it's also there is a matter more of having the right algorithm to do it. They have sophisticated algorithms which can do this very well. Yeah. So if you have, for instance, 2-dimensional nonlinear sigma models or CPN models and so on, for this you don't need supercomputers. Okay. Okay.
Sense.
Okay, sure. Okay, let's stop at this point. Yes. Okay.